this video we're going to go through how to work out Laplace transforms and inverse Laplace transforms using tables. So we have the table here, which is basically a conversion of the function and the transform. This is all done by the proof, but it's very complicated for some of these, so there's just a table for it all. So we're going to go through some examples of finding the Laplace transform using the tables. So we have the function t to the power of 3. If we look on the table, we have a function t to the power of n, and that's n factorial over s to the power of n plus 1. So the Laplace transform of the function is 3 factorial over s to the power of 3 plus 1, so 4. 3 factorial is 3 times 2 times 1, so it's 6, over s to the power of 4. If we keep going, we have sine 4t. We'll look at this side. We have sine wt w over s squared plus w squared. So the Laplace transform is 4 over s squared plus 16. If we keep going, we have t sine 70. So t sine 70. So the Laplace transform is 2 times 7 s all divided by 7 s squared plus 7 squared, and that whole thing is squared too. So we have 14s divided by s squared plus 7 squared. We have e to the power of 3t multiplied by t squared. So further down on the table we have this here. So the Laplace transform is n factorial, so 2 factorial, all divided by s minus 3 close bracket to the power of n plus 1, so 3. 2 factorial is 2, so we just rewrite s minus 3 to the power of 3. If you keep going, 6 cosine 2t, so we have here, cosine wt, so we can just multiply it by 6. So the Laplace transform is 6 multiplied by cosine 2t, so we have s over s squared plus 4, which is 2 squared, and of course we multiply, so we have 6s over s squared plus 4. For the next one, 3e to the power of 2t cosine 4t, so that would be this one. We have e to the power of 8t cosine 4t, so we can pull 3 out again as we did before, so that would equal to 3 close bracket s minus a, where a is 2, and that's all divided by s minus a squared plus w squared, which is 4, so 16. So we can also use the table to find inverse Laplace transforms. So the inverse is shown by the fancy L to the power of minus 1. So we'll look at this one, 5 over s plus 1, s squared plus 1, sorry. So what immediately jumps to my head is this one, because it doesn't have an s on top, it has an s squared. So we could easily pull 5 out. So the inverse Laplace transform of 5 over s squared plus 1 is 5 multiplied by sine wt, which would be 1, because we have on the bottom s squared plus w squared, s squared plus 1 squared, so it would just be t. The next one, we have 6 over s minus 2, so I'm thinking it's this one, because the s is not squared, there's no s's on top, and it looks very similar. So inverse Laplace, 6 over s minus 2, so we can pull 6 out again, so 6e to t, because we have 2 here, and it's minus a and positive a, so we've got to be careful with the minuses and positives. For the next one, we have 6 over s plus 1 to the power of 7. So for this one, I'm thinking that it's probably this one, because we have a neutral s here, and then we have a value, just a value, to the power of a bracket with a number. So e to the power of at, t to the power of n, and of course we have the 6 there. So the inverse Laplace of 6 over s plus 1 to the power of 7 is e to the negative t, because we have a negative a, positive a, so positive 1 is negative 1, e to the negative t multiplied by t to the power of 6, because we have a 6 on top, and 6 plus 1 is 7. The next one, we have s minus 2 over s minus 2 squared plus 16. So the one that jumps out to me is this cosine one down here. So we have s minus a to the power of 2 plus w squared, where w could be 4. So the inverse Laplace equals e to the 2t cosine 4t. And that's it. That's how you use Laplace transform tables.